Hello, welcome to this video. Today we're going to do the third part of the last two videos. So last video we found the formula for the area under a curve, and the second to last video was finding the formula for the derivative. And today we're going to, you can say, combine these two things, or combine a different way of doing them to get what we want to do, our goal. And our goal for today would be to find the length of a curve, a certain function in the x in the xy plane. So we'll have this curve, we'll call it f of x, and these two bounds a to b. And what we want to find is that you can imagine that this is like a piece of string. So, and then we stretch it out and measure its length. And that's what I mean by the length of a function. So let's uh, there's nothing that we need. There's nothing else we need to do other than jump right into it. All right. First thing I'm going to see is that this is hard length to measure. Like we have all this curviness, and it's just like last video where we had the area to measure was so ugly, and the simple way to and the simple shape to find the area of was a rectangle. And today we're going to use a similar thing. Uh, the length of just a straight line is very simple. If I can draw this straight, okay. Uh, okay. So yeah, the length of a straight line is very simple. Now this may look a bit complicated, but uh, let's call this point A and this point B. A small little trick we can use is drop a perpendicular into the x-axis from A and drop a perpendicular to the y-axis from B. So this is a right angle, and we'll call this point of intersection C. And AC is a easy length to find, YA minus YB. And the length of BC is easy to find. It's just XB minus XA. And then we use the Pythagorean theorem to find AB. But we won't be using that. We'll just be using the simple Pythagorean theorem. This is A, this is B, and then this is the square root of A squared plus B squared. Or A squared plus B squared is equal to C squared, or whatever you prefer. So, before we go on with that, I want to look at a little smaller recap of the derivative. So what was the derivative? Well, we took 2 points, A and B, on the function, and then we let their distance between the x values approach 0, and then used the formula for the slope of a line. Now, today we're going to look at it a bit differently. We're going to look at this line, and then again we're going to drop perpendiculars to the x-axis and y-axis from these 2 points. Again, we'll mark A and B. I'll mark this point at C. And the slope of AB in this case, or the absolute value of it, would just be the length of AC divided by the length of BC. Or, if you don't want absolute values, how much A go if you don't want absolute values, how much B needs to go right and then up, to reach A. In this case, it needs to go right a negative amount of times because A is on the left of B. So our slope will be negative, which gives us the formula. But we'll just be using this divided by this. Now, if we look at this as at the function, as A and B get closer and closer, AB becomes more and more of a straight line. And so we can easily measure AB's distance and AB's slope. And if we and remember, because they get closer and closer, the slope of AB, yeah, uh, slowly becomes the derivative, and it turns more and more like the derivative, which is something that we found in the second to last video about the formula of the derivative. And now we can think of AC as the small tweak between A and B, like this small distance d of the function because it's to the y-axis. So it's the meaning that it's to the y values. So I'll call this df. And then BC represents like the small tweak between A and B that approaches 0. As it just approaches 0. So that's dx, meaning that the slope of AB would be df over dx. And that's another way to write the derivative. The small tweak, where I have the small tweak and on the y divided by the small tweak in the x. And remember that dx represents the xa minus xb, the difference between their x values that approaches 0. Okay. Now, here's the trick that we're going to use again. Uh, Again, we'll have this same setup. A and B get closer and closer. And we'll measure the distance between A and B. And again, AB becomes more and more of a straight line and becomes more and more smooth. And these distances AC and BC are DF and DX. So we can use that to get the distance AB with the Pythagorean theorem, which means that the distance AB would be df squared plus dx squared. Now, we're going to take out dx out of this and then be left with the square root of df over dx, this thing squared plus 1. Or in other words, the square root of the derivative of f squared plus 1 times, now remember dx represents the distance between the x values of a and b that approaches 0. In the last 2 videos, we represented that same exact thing as h. So we'll just replace dx with h because they represent the exact same thing. And it'll be easier to work with h because we used that over and over in the last 2 videos. Okay, now let's erase the board. Now let's erase this and continue on with what we got. Okay, now here's what we're gonna do. This x represents the x of A or B, or whatever points A and B converge to together. Now you can think of this as if we have a bunch of these little lengths and then we add them all up, we get the length of a function. And it'll get closer and closer to the length of a function as these straight lines become closer and closer to the actual function itself. So this is what we're gonna do. For any x from a to b minus h, and I'll let you think a bit why that's b minus h and not where x is equal to b, we'll have to sum all of those distances up with this formula to get the length of the entire function. Now this is, remember, very similar to where we had our area, because then we'd have to split it up into rectangles, and their width would be h and the height would be say f of a. So the area of this particular rectangle would be f of a times h. And then once we had all those areas, we would sum them up. So h times the value of a plus h, a plus 2h, so on until b minus h. Sum it all up, and you get what you want. The area in this case. Or, in other words, the integral from a to b of this f of x. And here, what we have is h times a certain function. And then we have this function evaluated a plus h, a plus 2h, so on until b minus h. And then we need to add all of those up. And so we have basically the same thing as the area. So I'll call this h times g of x. And so we know that when we sum this up, because the bounds are a and b, we'll have to get that the length is the integral from a to b of g of x. It's like doing the area, but we already multiplied by the width, and now we just need to sum everything up. And we showed last video why this has to be the integral from a to b of g of x dx. Now just replace g of x to get at the integral from a to b of the square root of the derivative of f squared plus 1 dx, which I think is very cool because it is so close to just it is like so close to just being the function evaluated from at b minus the function evaluated at a. Because if we didn't have this plus 1, this would be just the integral from a to b of the derivative dx, which would just be f evaluated at b minus f evaluated at a, which would be the distance if f was a constant function. And in fact, if f is a constant function, this does become 1 because the derivative would be 0. And that's pretty much it. If you want more content like this, please subscribe to my channel. I'll be uploading more things like this in the future. And finally, that's it.